I think one of the things I like about thermodynamics is that when you study it, what we do is we very carefully analyze the different components that are part of what we are studying. Okay, so for example, we have something called the system. That's what we're trying to study. And then we isolate that completely away from everything else, either by equations or by physically putting barriers around them. And then there's the surroundings. Surroundings are everything else. Another way to look at it is in sort of a graphical system is we have our system, what we are studying, right? Now, this would be, for example, a chemical reaction, or it could be a chemical reaction in a solution, but it's whatever we're wanting to study. And it's going to be surrounded by the surroundings. And the surroundings in our um, scenario is everything that it can exchange energy with. So, for example, if you have a hot cup of coffee, right? Um, you could think of the mug and the coffee as being part of the system, and then everything else that it's exchanging heat energy with as part of the surroundings. Or you could just look at the coffee on the inside, and that's your system, and you're studying the energy transfer from that, okay? Or what we will be doing, okay, is we'll be looking at chemical reactions. We'll have a chemical reaction that takes place, and then we're going to study the chemical reaction and the amount of energy it produces by looking at everything that's surrounding it. Okay? And the important thing to recognize is that when you're studying a system and the surroundings, regardless of how you choose it, conservation of energy still applies. So if you can completely look at the surroundings and understand everything that's going on, then you can understand the energy of the system, because those two things have to be conserved. They have to add up to always be the same amount. Now, technically speaking, what we're doing in our study is looking at something that's called a closed system. And closed systems only exchange energy. Now, what if it was an open system, right? If it's an open system, then all kinds of stuff can transfer. Matter can transfer, energy can transfer, um, gases, things like that. All kinds of stuff can transfer. And then we also have something we call isolated systems. You don't particularly need to know those, but if you know what a closed system is, can only exchange energy, then an open system kind of makes sense, and an isolated system also makes sense. It's nothing is exchanged. Okay, it's insulation around your system, nothing being exchanged with the surrounding. So a closed thermos would be, and if you're calling the liquid inside the closed thermos, or let's call it a what's the popular one? A Yeti, right? You have a Yeti, then the liquid on the inside of your system is completely isolated with the surroundings. No, there's very little energy transfer, and no, unless you open the top, no matter transfer from the inside to the out. So the next important thing to understand is the relationship of system and surroundings in terms of energy flow. Okay, so the system is exchanging energy with the surroundings. So let's say the system is losing energy. That means the change in the system's energy will be negative, right? Because it's losing energy. And then if, again, the surrounding is everything it can exchange energy with. So if you're trying to think of things that can't be part of the surrounding, basically nothing falls in that category, because the definition basically says everything, right? But then the surroundings is picking up energy, right? And so we can think about the surroundings energy flow being positive. So I like to think of it like this. This is me, right? And this is my son, Andrew. And I have money in my hand, right? And so my energy flow, money is a great, by the way, token to think about energy flow. Energy flow goes like this. So, all right, I'm losing money. I'm giving it to my son. But here's the thing. My net worth, my system, I'm the system. My energy is going down, right? My son's energy is going up. Now, if you took this and you added them together, what's the change in energy? Well, there is no change in energy total because what I lost is exactly what he gained because I gave it to him. Energy is conserved. So the system's energy is one value, but the surrounding energy will always be the opposite value. What happens when you add those two things together? The net change in energy will be zero because energy is conserved. We can do this same argument or sort of discussion the other way. Okay. Let's say, again, I'm the system, right? And yeah, I won't take money from my children. Let's say this is the school. I don't know why this is what school looks like, but this is what school looks like there. And they give me money, right? And I'll make it big money. That's what my kids used to call it. There's my big money. I'm getting big money. So the surroundings are now giving me energy. So my energy is positive, right? My net worth has gone up. The net worth of the school, right, has gone down. They've given me money. Of course, they've gotten work in exchange, and let's not get too detailed about this, but they've given me money. The net change total, if you add these two together, what's the net change, right? The net change is zero because there isn't any loss of money, unless you're considering taxes as the loss of money, which it kind of is, but they're giving me money, and assuming no taxes are taken out yet, right? I'm getting the money. The total amount of money doesn't change. Again, the system, we would write it still, has an energy change that's opposite of the surroundings. Exactly what we have wrote for the other situation, okay? Now, again, system plus surroundings, no loss of energy. Energy is conserved. Okay, so for the system, I want to describe a new variable, okay? And I'll talk about what a state function is in a little bit, but E is going to be something that's called a state function. And it is, for the system, it's the system's kinetic energy and potential energy. So it's the sum of those two different things. So if I want to know the change in the internal energy for the system, that's known as delta E. Okay, delta E is the change in internal energy. Now, change in anything is always calculated as the final state minus the energy of the final state minus the energy of the initial state. But that's true for anything. So change in temperature is the final temperature minus the initial temperature. Now, thinking about what's going on here, right? This is the system, right? The system gained energy. What does that mean in terms of delta E? In terms of delta E, it means it will be that the final state will be higher in energy than the initial state to give us a positive energy change. On the other hand, in this case, right, I was the system still. I was giving money to my son. My energy change was negative. So what does that mean for delta E? For delta E, it means the final state has to be a smaller value than the initial state for me to get a negative value. And when I just realized that this is it's not a negative, it's a bullet point thing, and I should have just not used that as the bullet point. Anyways, so change in energy is the final state minus the initial state. The sign, right, delta E sign, gives us which way the energy is changing, whether or not you're going from a state of higher energy to lower energy. That is, you're losing money, right, or losing energy, going from high to low. Or if it's positive, then you're gaining energy or you're getting money, right? So you're going up in your net worth And so you're absorbing energy from your surroundings. Now, this is the application. I actually had this on the wrong slide before, but we have products and reactants in this reaction. Now, this goes along with the final up here, not with this reaction that's down here. So here's my products, right? This is my final state. This is my initial state. This is my reactants. Okay, so this is an example of a combustion reaction for coal. Now, coal is just pure carbon, and you can light it and burn it with oxygen, and it produces carbon dioxide and heat. Okay. Since heat is being released, I know that the final state must be lower in energy than the initial state, because that heat energy is a form of kinetic energy that was released from the potential energy of the molecules in the reaction. So my reactants react, they give me a product, energy is released, and I get a heat, right? I get energy released, which means my final state is lower than my initial state. And when you're drawing what's called an internal energy diagram, or sometimes just called an energy diagram, all we do is we list the reactants in terms of their energy and the products in terms of their energy. And when you're going in the direction of C solid, carbon or coal, and oxygen to CO2, you're going down in energy, right? There's a loss in energy, so delta E is negative for your system, okay? Well, of course, it also means your surroundings are absorbing that same amount of energy. So I ran out of space on the last slide, so this was actually supposed to be on the last slide, but there's no room for it. So for the reaction of the carbon, right, the coal plus oxygen to CO2, we would say that this reaction is exothermic, that energy is being released, okay? Exo, outside, thermic, heat, right, heat energy. So heat energy is being released in that reaction. Now, you could also write the reverse of this reaction, and when you write the reverse of this reaction, what actually happens is you change the direction of the arrow from actually the original arrow was carbon plus oxygen makes CO2 in this direction, and that is a release of energy. And then when you have the reaction in reverse, actually you're just taking the arrow. These don't move in terms of their relative positions, but what you do is you change the direction of the arrow. So delta E is positive because you're starting at low energy, that is the CO2, and going to high energy in terms of carbon and oxygen up here. So this type of reaction, delta E would be positive because this is your initial state, and this is your final state. Delta E is positive because the final state is above the initial state, and we would call this type of reaction an endothermic reaction. It absorbs energy, endo, bringing in or within, thermic just means heat, brings heat energy in to make the products.